What really happens when code runs? You write instructions, compile them, hit run. But between your command and the machine's action lies a perfectly choreographed dance of electronic signals. Today, we're uncovering that dance, the story of how CPUs and memory actually communicate. At the heart of every operation are two key players, the CPU and memory. The CPU is the thinker. It needs to fetch instructions and data from memory to do its work. But here's the question. How do they talk to each other? Step 1. Specify the location. To fetch data, the CPU must first provide a precise address, like telling a librarian exactly which shelf and book you need. In this case, the CPU wants data from location 101. This address signal must travel from the CPU to memory. Enter the address bus, the unidirectional GPS of the system. It carries the memory address from the CPU to either memory or input-output devices. The key word here is unidirectional. The CPU always generates the address, and memory only receives it. The width of this bus determines how much memory the system can address. Here's why bus width matters. A 3-bit address bus can access 2 to the power 3, which equals 8 unique memory locations. The classic 8085 microprocessor had a 16-bit address bus, giving it access to 2 to the power 16, which is 65,536 locations. The wider the bus, the more memory you can reach. Step 2. Issue the command. The address is set, but what does the CPU want to do at that location? Does it want to read data from it, or write new data to it? Memory needs a command. This is where the control bus comes in, the conductor of the operation. It carries control and timing signals from the CPU's control unit. These signals orchestrate the entire operation, telling all components what to do and when. Example signals include memory read, memory write, load register, and clear. Step 3. Transfer the data. With the address known and the read command received, memory is ready. The final step is to move the actual data back to the CPU. This requires a dedicated pathway, a highway for information itself. Meet the data bus, the bidirectional highway. It carries actual data between the CPU, memory, and input-output devices. Unlike the address bus, data flows both ways, from memory to CPU on a read operation and from CPU to memory on a write. Its width defines the word size, how much data transfers in a single operation. A 16-bit data bus can transfer a 2-byte word at once. Let's synthesize. Step 1. The CPU sends address 101 on the address bus. Step 2. The control bus carries the memory read signal. Step 3. Memory finds location 101. Step 4. The requested data travels back on the data bus to the CPU. 4 coordinated steps, 3 buses working in perfect harmony. To reinforce this, let's look at a write operation. Step 1. Address 101 goes out on the address bus. Step 2. The actual data to be stored travels on the data bus toward memory. Step 3. The control bus sends the memory write signal. Step 4. Memory stores the data at location 101. Same buses, different direction, different command. This interconnected system of buses forms the fundamental communication pathways of the computer. The address bus points to locations. The data bus carries information. The control bus orchestrates timing. Together, they coordinate every action between the processor, memory, and the outside world through input-output devices. Mastering the bus system isn't just about hardware. It's the key to truly understanding how software translates into action, why memory access patterns matter for performance, and how a computer works as a cohesive whole. You've just learned the language of the machine. If this clicked for you, hit subscribe, because we're just getting started. Thanks for watching.